Welcome to the MPCA's Production and Quality School, Level 1. This course is intended to cover the essentials of precast concrete production. In this introductory chapter, we're going to discuss the desirable properties of fresh concrete. Then we'll talk about concrete in its hardened state. Then we'll conclude the introduction by looking at the essentials for producing quality concrete. Throughout this course, we'll be referring to concrete in two basic stages: fresh, meaning it has been mixed and batched and is still workable. Hardened means the concrete has achieved initial set and can no longer be modified. First, let's start with the desirable properties of fresh concrete. What are things that we're interested in? We're interested in consistency, workability, and uniformity. And we'll talk a little bit about bleeding rate as well as finishability. We'll discuss controlled setting times and then look into temperature. Consistency. What do we mean when we say consistency? Well, of course, there's the definition that says relative mobility of the concrete mix. When something is relative, we've got to relate it to something else. There's got to be some other benchmark. So typically, when we're talking consistency, we're referring to consistency from batch to batch. Every time you make a batch, you want it to be consistent with the previous batch, especially if you're pouring, for example, a large structure and you might put multiple batches into it. Consistency is typically measured using the slump test, or if using a self-consolidating concrete mix, the slump flow test is used. There is a common misconception in the precast industry that slump test or slump flow test is a measure of the amount of water contained in concrete. This is not true. There are numerous factors that can affect the slump of concrete, such as admixtures, aggregate shape, temperature, and so on. Therefore, it is important to remember that slump or slump flow is a measure of consistency, not water content. Workability, also referred to as placeability, describes the amount of effort it takes to place concrete in the form, consolidate the concrete, and then finish the concrete while avoiding segregation. For those of you not familiar with the term segregation, it refers to coarse aggregates sinking while the fine aggregates and cement paste float to the top of the form. When this occurs, the concrete mix is no longer consistent or homogeneous. Therefore, segregation is highly undesirable. Workability can be affected by many factors. Some of the factors that affect workability are temperature, water content, supplemental cementitious materials, and admixtures such as air entrainers, water reducers, and superplasticizers. Good uniformity means that all portions of a single batch will contain the same proportions of the same ingredients. To clarify, when we talk about uniformity, we're talking about having the same proportions in all portions of a given batch, as opposed to consistency, which means having the same properties from batch to batch. Uniformity is affected by factors such as the quality of constituent materials, proper mixing, transport techniques, and production practices. You may have noticed that after concrete is placed and finished, water may come to the surface of the concrete. This water is known as bleed water. The bleeding rate is a measure of the migration of the bleed water to the top surface of the concrete. The amount of bleed water in a given concrete mix can be reduced a few different ways. First, the less water in the mix, the less bleed water we will have. As we'll see later, when we talk about water cementitious material ratio, less water in concrete is a good thing. Also, the more fines, or fine aggregates and cementitious materials in a mix, the less bleed water you will have in the mix. When finishing concrete, it is important not to finish concrete while the bleed water is still moving to the surface. Finishing during this time will force the bleed water back into the concrete. This will weaken the concrete surface layer and may also cause scaling. For those of you who have had the opportunity to finish concrete, you know that it is an art more than a science. It can also be much more difficult than it looks, depending on the concrete mix that you're working with. You need to take care not to perform the final finishing before the bleed water has had an opportunity to evaporate. Finishing processes can vary greatly depending on the desired final appearance. Some common finishes are form finish, steel trowel, and wood float. There are also a number of more exotic architectural type finishes such as sandblasting, acid etching, exposed aggregate, but these finishes typically occur once the product has had a chance to cure and has been removed from the form. Some factors that affect the finishability of a concrete mix are the water-cementitious ratio, proper mixing, transport, and temperature. Concrete setting time is important to precasters. The faster concrete sets up in the form and reaches the specified stripping strength, the faster the form can be stripped, cleaned, and set up for the next pour. What do we mean by setting time? Well, there's a difference between setting and hardening. Setting time refers to the loss of workability. It is the stiffening of the concrete mix. When we talk about hardening, we're talking about strength gain. There are two types of setting times that we typically look at. They are initial setting time and final setting time. Initial setting is the time from the addition of water until the mix ceases to be fluid. ASTM, the American Society of Testing and Materials, defines initial set as the time it takes for a concrete mix to reach 500 pounds per square inch. Final setting time is the time from addition of water until a certain degree of hardness or strength is reached. ASTM also has a definition for final set, which is the time it takes for a concrete mix to reach 4,000 psi. It's important to note, when talking about temperature, that we're talking about the temperature of the concrete mixture itself. Concrete temperature is very key because, as we have mentioned previously, the temperature of the concrete can affect the workability, consistency, and even the hydration of the cement. For most concrete mixes, 50 to 60 degrees Fahrenheit is the ideal temperature for placing concrete. ASTM even has a test method for taking the temperature of fresh concrete. Now let's move on to the properties of hardened concrete. Now we're talking about concrete that has been mixed, placed in the form, vibrated, finished, cured, and allowed ample time to reach a final set condition. In this section, we'll discuss the desirable properties that we're concerned with for hardened concrete. Durability. When most people think of concrete, they would say that concrete is a durable material. But what does that mean? One way to think of it is when a concrete product is placed in some sort of exposure environment, how long will it last? Durability is also defined as the ability to resist internal and external attack from things like chemical attacks, freeze-thaw cycles, alkali silica reaction, ASR, and delayed ettrinite formation, DEF. Concrete mixtures can be altered using admixtures, supplemental cementitious materials, or lowering the water-cementitious ratio to make them more durable to their destined environment. Is good quality concrete watertight? The answer is yes. Although concrete is a porous material, we can control the size and disbursement of those pores through water control, aggregate gradation, admixtures, and proper curing and consolidation, thus controlling the concrete's permeability, or the speed at which fluid makes its way through the structure. We can slow that speed down to where it could take hundreds, even thousands of years to traverse a 6-inch wall. We can also enhance concrete's water tightness with sealants. Here is a photo of the Magdeburg Water Bridge in Germany. As you can see, the Magdeburg Water Bridge is made out of concrete and appears to be very watertight. Concrete strength is discussed frequently in the precast industry and the concrete industry in general. But what exactly does it mean when we say we are making a 3,000 psi or 4,000 psi concrete? Well, typically we're talking about the compressive strength of the concrete. As we'll discuss more in depth later in the course, concrete is strong in compression and weak in tension. So when we say we have a 4,000 psi concrete, that means that we could set a 4,000-pound weight on a 1-inch by 1-inch square area of concrete and the concrete would be able to withstand that force. Concrete's compressive strength is affected by the water-cementitious ratio, aggregates, and production practices. Now, how about abrasion resistance? What we're talking about is the ability of concrete to resist rubbing. Some examples of situations that may cause abrasion to concrete are traffic from motor vehicles or people walking across a concrete floor in a busy walkway. Water running over concrete can also abrade concrete surfaces. Precast concrete can be made to be very resistant to abrasion by using quality raw materials and proper manufacturing and placement practices. The appearance of our products is also a very important part of what we do in the precast concrete industry. Product appearance is dependent on the concrete properties that we discussed thus far, such as workability, uniformity, and consistency. However, good production practices and having a sense of pride in your workmanship are the two biggest factors that affect product appearance. We all know that appearance is important for architectural products. Appearance is equally important for underground products as well. Imagine two septic tanks sitting next to each other. The one you made, which looks beautiful, no bug holes, no pore lines, all the corners are crisp and clean. Now imagine a septic tank sitting next to yours that someone else made that has honeycombing in the corners, surface rusting from rebar touching the formwork, pore lines at various locations around the structure. Which septic tank do you think a homeowner or other person buying that tank will buy? Appearance is the first impression of quality, no matter where the structure is being placed. Let's discuss dimensional stability. Concrete moves volumetrically, although not as much as some materials. Actually, concrete, compared to many of the building materials out there, is fairly dimensionally stable. It moves volumetrically for a variety of reasons, such as thermal change, moisture change, and even molecular change. You might have heard a term called creep. It's a situation where basically, if you put a stress on something for a long period of time, it will actually start to force a molecular reorganization in there. That shelf in your cupboard that holds all the big cans of soup, beans, and cream corn, for example, will change in shape after a few years. That's something we take into account when we build tall skyscrapers. The ones we're more concerned with are the things like drying shrinkage and subsequent cracking. You can improve the economy of your concrete by optimizing your mix design. We will be going into much more detail on this as we keep moving forward through the chapters, but if you're using, for example, more cement than is necessary to speed up curing, perhaps you're spending a lot more money than necessary. And if you optimize that mix design, you'll be able to save yourself some money on those costs, and you can actually even apply that all the way through the plant, in every manufacturing procedure. The processes that we discuss throughout the course will certainly help to improve the quality of the products, but you may find that some of them will even save you money. Making a quality product is like a chain. Think of each link in that chain as a step in the process, from obtaining and testing your raw materials to placing the finished product on a flatbed truck. The chain is only as strong as its weakest link, which means all these processes are key to a quality product. For example, if the reinforcement is set up incorrectly and is placed wrong, it doesn't matter how well the concrete is consolidated and finished. The piece will not function as it was designed to function, or how the owner intends for it to function. As this course progresses, we will discuss how suitable and consistent materials are an essential part of making quality precast concrete. Proper design is very important. As precasters, you will be involved in some aspect of that design. You may be assembling and placing steel, or you may be working the batch plant, or you may be putting in the blockouts. Either way, you're involved in that design of that product. When the engineer of record designs the structure to have a piece of rebar in one location, there is a specific purpose and function for that piece of reinforcing. The engineer has done his job. Now it's up to you to do yours by ensuring that the drawings are adhered to. 1/2-inch deviation can mean a structural failure. During this course, we will go into proportioning, mixing, and transportation of the concrete. Following the specified mix design may be easier now than it was 20 years ago due to automated batching systems, but it's still important to monitor all quantities. Also, many plants have multiple mix designs, as high as 30. The right mix design for the job is key. Allowing adequate mix time, but not too much mix time, is essential. And then, how you get the concrete from the mixer to the product can alter its properties. Taking a bucket of concrete 150 yards across a bumpy yard can cause some serious segregation within the concrete. Repeatability of procedures will ensure consistency of results. We'll talk about forms and how to care for them. We'll also go in depth about consolidating concrete, finishing concrete, and the all-important curing of concrete. We'll look at different types of curing and the reasons why we cure. This concludes the introduction portion of the MPCA PQS Level 1 course.